Swayam Prabha. Digital India. Educated India.
So, welcome to the third lecture, and this is the continuation of the second lecture, thermal properties of the material part 2. So, we will discuss in this particular module, in this particular lecture, three things. One is the heat gain through radiation. If you remember, the last lecture we discussed about the conduction, and we also will discuss the solar heat gain factor, and also we will discuss the solar temperature. This radiation, if I see, we get the solar radiation, and that solar radiation is actually going to involve in the heating the different objects. It will first this radiation heat will actually fall upon the building surfaces, roofs, different wall, the windows, and due to that particular radiation and some of the radiation may penetrate through the windows or the glazing or the skylight, and finally it will accumulate inside the room, and that will be the room will be the temperature will increase, the total thermal gain, the heat gain also will be increased. This particular radiation, solar radiation, is different in different surfaces. So, if I see what are the factors that actually vary, that gives the variation in the solar radiation in the different part of the globe, is first of all the latitude. So, in the latitude point of view, if you go in the higher latitude zone, the inclination of the sun's angle is not perfectly 90 degree, or it will be much more, and that is why the amount of radiation will be low. The time of the day, so it is the daytime the radiation is exposed, the solar radiation is exposed to the portion of the earth, and which time you are considering. Are you considering in the very early in the morning? Are you considering the late in the evening, or you are considering the afternoon time? So, that is another point. Then the altitude, then it is in the sea level, or maybe it is the same the latitude, but not in the sea level, it is in the hilly area. So, that is also going to be the deciding factor. Seasons, the same location, same time, maybe you are calculating at maybe around 12 in the afternoon, same altitude, but in a different day, in a different season, not in the month of May, or maybe it is month of December. So, things will be change, the amount of solar radiation comes to your is this change, and also the amount of cloud cover. So, if you see the NBC, the National Building Code 2016, also it was given in the 2005, the same chart. It has given the solar radiation in summer and winter in different orientation. So, that means, as you know, in the northern hemisphere, sun moves from the near about northeast or maybe around east, and then it follow the southern path and southern side, and then the west. So, there is a variation in the south intensity, variation in the east intensity, variation in the west wall intensity, also in the north and also in the horizontal. So, here north, northeast, east, southeast, south, southwest, west, northwest, and horizontal, all the 9 surfaces, 8 coordinal surfaces and 1 the horizontal surfaces, both in summer and winter. And in this 1, 2, 3, 4, 5, 6 latitude, 9 degree north to 29 degree north, it was listed. So, this is very helpful the data. So, we can take this data if my city is nearby, may not be exactly on 13 degree, but we can see that yes, it is approximately in that area. So, we can actually see if my southern side I have this much of area. So, how much is the per day watt per meter square per day is again. So, here we can understand one thing, the solar radiation is given with a unit of watt per meter square. How much watt per meter square of the area is falling, I mean then how much joule per second or something like that. So, that is one of the points. So, now the solar radiation, the variation in the various surfaces if I want to see. So, this is the north surfaces, we are in the northern hemisphere. North is not at all directly exposed to the directly sun, maybe in the some part of the morning, some part of the evening or whatever, maybe it is under a diffused kind of a radiation. So, it is very minimal kind of a thing. So, from morning 6 a.m. to the evening 6 p.m. if I want to see. So, this is the south surface which is potentially high, because a predominant time of the solar path is actually follow the south, or the incident, the radiation will be on the southern surface. The next one is the roof surface, which is horizontal, is the maximum, the peak, because the horizontal surface from the morning 6 to the evening, whatever may be the sunset, sunrise to the sunset, it is always exposed to the sun. But if see all the three, it is not constant, it is increasing and then there is a decrease. So, that is there is again a periodicity, Now, east surface you see it is morning sun. So, by around 12 or so it vanishes, that particular sun rotates and then it goes to the west side or so. Similarly, the west surfaces are some other type of the hump, other side of the afternoon side. But what I see, all the five sides are the horizontal, including the horizontal, there is a time dependency, the solar radiation is not fixed. So, we will discuss how to tackle that one, because if I want to actually accumulate that how much heat is penetrating because of the temperature difference. We have seen in the last lecture that there is the periodicity exists in the temperature, outdoor temperature also, and now we are seeing that there is again a kind of the periodic phenomena is also exist in the solar radiation also, because solar radiation is also going to impart a lot in the heat penetration or the total cooling load calculation. These two periodicity, and this periodicity is different, the east wall periodicity type of periodic changes and the west wall is not same, and east west is not going to be the same with the south and the roof. So, how to tackle that one we will see. Of course, it is required little bit of higher mathematics, but we will not go in that much of detail, we just see that how easily we can develop some kind of a approximate kind of a model, and that will actually calculate the heat gain through a building in the maybe the third phase or the fourth phase of our lecture. So, pyranometer is another instrument which actually used for the estimate this radiation. So, nowadays digital pyranometer is available. Now, when we a particular glass or maybe a particular glazing or any transmittance kind of transparent kind of the material is exposed to solar radiation, there is some incident solar radiation which going to be incident upon a glass. Some of them, some of the portion I must say will going to reflect it back, some definitely going to transmit, some of the portion will actually absorb inside the glass, and after absorption a amount will be going to transmit and amount will be going to out. So, by virtue if I see the what is my total incidence and what is my total gain inside, that is a direct transmission which is this arrow, and the second was absorption in, that means this red arrow is my actually gain inside the building. So, this ratio is very important, because this ratio will give you a kind of a character of a glass, that how much amount of radiation is actually transmitted in and also absorbed in. So, how much is my gain inside the building, inside a particular room, how much is this. So, this particular ratio is called solar heat gain factor, solar heat gain coefficient, SHGC. This is sometimes also called as a solar gain factor, SGF also. So, solar heat gain factor is a unitless quantity, gives you a particular ratio, that if the ratio is, suppose it definitely fluctuate between 0 to 1. If everything is blocked, nothing is transmitted, nothing is absorbed, it is 0. And if everything comes in, nothing is reflected, nothing is absorbed out, then it is 1. So, both may not be occur any, there maybe it will occur in between. Suppose it is maybe 0.6, that I mean to say that 0.6 means 60% of the incident radiation is actually comes in, and 40% is whatever out, right. So, if the SHGC, these SHGC values are very high, definitely it will admit lot of radiant heat, and vice versa, if it is low, then it will be very good, for it will not going to admit. So, this is the I have discussed already. So, now if I see a heat conduction through the window, how it is happening. So, it is happening in two ways, one is through conduction and definitely one through the radiation. So, there is a temperature gradient exists. So, this glass, the window glass or maybe the glazing is also having a material, envelope material having some thickness, maybe very low, but still some thickness. So, there is a temperature gradient exists, and this particular the material has a U value. So, based on that I can easily calculate the conduction, how much is that. We have seen in the last lecture that we have calculated, if I know the area of the exposed window, if I know the U value of the window, and if I know the temperature difference. Similarly, I can also find out how much is the radiation heat gain, because the wall and the opaque surfaces will not allow any radiation, only the transparent surfaces like the glazing or the window will allow. So, in that case my equation will be the area into the SHGC multiplied by the I, where I is the amount of incident radiation. Now, you see that incident radiation is nothing but your watt per meter square. If your window is in southern face, at some time, some date, it will have some kind of incident. So, you have to see that how much is the I value, and this I value is ever changing from the, in a day it is changed from morning to evening, in season it is changing. So, this I value is a kind of fluctuating value. So, we can take average and we can do something like that, but if I have a window and if I want to use that in that particular my heat load calculation, I have to use that particular window because it is in the envelope surface. I have to take two type of the heat that comes through the window. One is conduction. So, I have to use this equation and I have to use this equation also. So, these are some of the U values and the SHGC values are mentioned for tinted glass and some of the clear glass. So, if it is single glazing, that means only one sheet of the 6 mm glass, the SHGC is 0.76, that means 76% of the radiation is actually transmitted in and also the absorbed in. Whereas, a clear glass of double glazing, where the two glazing with some air gap, so it is 64% or 0.64. Now, if I go with the body tinted glass or the surface tinted glass or the reflective glass, I have mentioned the definitions of those. So, the values dropped. So, from 0.76 to it is 0.6, 0.5 to 0.18, as and when the SHGC value drops below, below maybe 40% below that, is always going to be a good, because In case of the reflective glass, you see it is 0.18, that means 18% is admission or transmission in and the rest is going out. So, here in the double glazing surface tinted and plus clear. So, there is a double glazing, one is surface tinted and plus one is clear. So, one is body tinted and one is clear and one is reflective glass and one is clear. So, like that I have taken those values from this particular source. So, you see when there is a radiation and this through this radiation when is actually fall from the sun actually comes, sun rays will comes with only short wave radiation. What is short wave radiation? If you see the electromagnetic spectra, there is a visible light, we will come to that just maybe 2-3 slides after. So, this radiation is a infrared radiation. Infrared has a very broad band. So, out of that the short wavelength is actually comes from the sun and it will actually fall into the glass. Now, short wave radiation goes in, and this long wave radiation, the other part of the IR radiation is actually not comes from the sun, but it is actually emitted by the glass because of the glass become hot because of the short wave radiations also. So, that is why I have written over long wave re-radiation. It is not the original, because the glass has been heated up, the temperature of the glass surfaces has been heated up, or any surfaces if it is heated up, you will get the radiation, that is the long wave radiation. So, long wavelength part of the infrared spectrum. So, we can stop that one, we can manage, somehow we can manage to stop that one, and in this long wave radiation stay indoor because it cannot go out, it will reflected inside the indoor, and that is why if there is a glass building also we say it is a greenhouse effect. It is going to be gradually heated up and the temperature is increased be very high, because it is cannot go out, this long wave radiation which is trapped in, it cannot go out. So, somehow we can actually do something by virtue of some material science way, that some coating can be given in this particular surfaces, glass surfaces, such a way that this emissivity, what is emissivity? Emissivity is a property of a material to radiate the heat energy. So, if I put some protective layer or some kind of other material, that will not going to emit, that will not going to radiate that much. So, automatically the long wave radiation will be less. So, that kind of the low this low emissivity material we can think of, and it is available in the market. So, the low, that is called the low E glass. So, low emissivity glasses, little bit high cost of course, but that is available, which actually allow the short wave radiation, and but it will stop the emissivity of the glass itself, so that it cannot, or it will not going to radiate long wave that much. So, now let us see with this help of these equations how can I find out some of the heat gain also. So, I have a wall whose dimension is almost 60 meters square, 15 by 4. WWR is 15%, window to wall ratio is 15%, and wall U value, window U value, and window SHGC values are also mentioned. Wall does not have any U value, as you know, it is opaque. The outdoor temperature and the indoor temperature are also given, and solar radiation I have mentioned as 150 watt per meter square. So, first of all I need to know the how much is the wall area and how much is the window area. This window to wall ratio is going to help me. So, I found out that 9 meter square is the wall area and the 51 meter square is the window area, fine. So, I take it to the next slide. So, wall area I know, window area I know. So, now I will take the first equation to see how much heat is conducted by virtue of conduction through wall. So, I have that old formula which we have discussed in the last lecture. The area of the wall is 51, the U value is 3 that I have mentioned over here, you see, and the temperature difference is this. So, this the 2142 watt. Then similarly, I do the same use the same equation for the window, because window have now two component, one is through the conduction of the heat and another one is the radiation. So, here very simple, A is the 9 area, the 5 is the U value of the window which has been given in the problem, and the del T remains same, and this is 630 watt. And then the last one, the other part of the window, the radiation part of the window, where this new equation I have to place, the area of the window is 9, SHGC of the window is 0.6. You see the SHGC is 0.6 has been taken here, and there is no question of del T. Instead of the del T, the outdoor temperature is the nature given. So, here I have taken another nature given parameter, which is the solar radiation 150, that is 150, and this is 810 watt. So, now I have to add it up. So, if I add it up, I got the value as 3582 watt. So, it is 3.5 almost 3.6 kilowatt is the total. That means, for that particular situation, when your temperature is 38 degree outside, you want to keep yourself as 24 degree. That is why I call that as a indoor set point temperature. I want indoor as a 24 degree centigrade. At that particular moment, the solar radiation is 150. You have a wall of 60 meter square with 2 windows or 3 windows, whatever it may be, but only 15% area of the window, and rest 85% of the area is your wall. I think so. I just go back. Yes, WWR is 15%. So, 15% is your window, and the rest of the area is your wall. So, at that snapshot time, 3.582 kilowatt will be the energy transmission. Then next is a very important thing, is the solar temperature. See, because of the solar radiation which actually strikes in the surfaces, the surface temperature increases. If you just touch a wall which is under the solar radiation, and another wall, the same material, same color, same thing, but it is under shade, definitely the wall which is under solar radiation will be higher in temperature. So, we have to take that particular into account, because the conduction of the heat from the one surface of the wall to the other surface of the wall. So, this surface wall condition I have to see, it is not only the outdoor temperature, but also this temperature of the wall surface. So, is it under shade or is it under solar radiation, direct solar radiation, that has to be seen. So, we have to find out this solar air temperature, which we will find with this particular formula. You see, this is the outdoor temperature TO, it exists, and a additional extra amount of temperature can be found out by the solar radiation, which is I, then absorbent of the surface, which is small a, which how much it is going to absorb because of the color. If it is, again, if you see, both wall are under sun, but one is black in color, one is white in color. Definitely the black color surface will absorb more, and you will see the little bit extra temperature. So, the value of the absorbent, it fluctuates from 0.1 to 0.9. So, that is also there, and also the surface conductance, how surface is conducting the heat, that is also a very the interesting phenomena, because of the thin layer and the some of air or so, it is also going to. So, that value is also depend upon the material. So, that value is given in watt per meter square degree C, and that value comes from 15 to 25, around 15 to 25 watt per meter square degree C, depending upon different type of material. So, now suppose the wall is under shade, complete shade. So, then the I is going to be 0, and as and when I is going to be 0, you will have the solar temperature equal to the outdoor temperature, 38 degree, whatever we have seen in the last example. But if there is a 150 or something is there, some solar radiation is there, because of your color and all these things, there is a and F naught exist, because of those parameter, and there will be some increment of your the temperature, and this two temperature will add up, the increment plus the outdoor temperature, and that should be, you should take that for your calculation. So, let me see with the same problem which we have solved just now. I have just given two more data, that the surface absorbent is 0.4, which is A, which is, this is your A, and the surface conductance is 20, which is your F naught. So, the same problem, so that this area calculation remains same. So, we will go back to this. We have now have to calculate how much is your solar temperature. So, your radiation is 150, the same which we have taken in the last problem. This is your A value, this is your F naught value. So, almost about 4 degree. So, this, if you see that there is a 4 degree. So, this is 38 plus 4 degree centigrade is increment because of this solar radiation. So, if you have to take as outdoor temperature 41 degree, not 38 degree. So, if you take 41 degree, because it is under solar radiation, your calculations will be much more accurate. So, based on this, again I am calculating the heat gain through the wall, which here I have taken the solar air, not outdoor. So, now it is not 38 minus 28, and it will be now 41 minus 24. So, this is the value in the conduction of the wall. Conduction of the window, again this is 41 minus 24, that 18 degrees or so, and your other values remain same, the area remains same, your U value remains same, only the solar air temperature changes if it is under sun. And the last one, that 810 will be remain same, because in this particular equation, the radiation equation, there is no question of any temperature difference or so. So, I will get almost about the 4.1, if you remember last one it is 3.5, this is 4.176 kilo or so. It is has been a kind of increment, definitely it has to increase, because we are considering the solar radiation, we are considering the extra temperature raising in the outdoor wall and outdoor window surfaces, which actually contribute to the transmission of the heat. So, we have different type of protective material, we can use those protective material, we have insulative, this EPS covers, or the sometimes some hollow concrete blocks, or some kind of the layers which can use for the protective material. So, we can use that in our building. There are some cases, this is the EPS, this is the EPS, and sometimes we also put some kind of protective materials in the rooftop. Also, we will try to put roof light in color, so that the reflectivity is increased, the absorptivity, this A decreases. So, solar air temperature decreases. You see in the hot sunny day, you cannot walk in the roof terrace barefooted probably, because its temperature is much more higher, the solar air temperature is much more higher. Maybe the temperature outside is 38, 39, 40 maybe, but you cannot walk in the afternoon, maybe 2 o'clock or so in the terrace, because of the surface temperature of the terrace is maybe around 55 degrees or so, 15 degree high, because of those parameters, solar radiation very high, maybe 800 watt per meter square. So, that particular temperature has to be taken, and that particular temperature will be killing you because of the heat transfer kind of a thing. So, how that can be reduced down, maybe shading, maybe some kind of this insulative material. So, those are some of the EPS, the expanded polyolefin material is very useful for this purpose. So, now how I can use it? Suppose I have there are two materials, one, suppose the combination, suppose the UA is your RCC slab, which is, suppose your U value is 3, and UB, the new material you are putting up, and that is your next new material, that is your 1 inch extended polyolefin, which is having U value of 1. Then what will be the combined U value of these two layers? So, that you can use this equation, it also can be a very approximate equation, but holds very good. So, the combination of the U values of the material A and material B will be reciprocal, add and then again reciprocal it. So, 1 upon UA plus 1 upon UB. So, 1 upon 3 1 upon 1, and then see the actually if you want to use a RCC roof, that U value is 3 and it is dropped down to 0.75. Now, instead of 1 inch EPS, if you use 2 inch EPS, then the U value of 2 inch EPS is 0.6, is further dropped. So, you will get a maximum benefit by virtue of this insulative material. Insulative material increases the thicknesses and all, and also impart the decrease in the U value, which will be helpful. Now, here it is the energy efficient glazing, as I told you. The glazings are there, the glazings, window glazings are also required for the daylight. So, the solar, the radiation also take care of your visual light also. So, if you see the band, this is the band for the solar spectrum. It has a infrared portion, it has a visible light portion, it is a UV portion also. So, out of that, this 44% is the visible light and 53% is the infrared, which is actually heat. So, out of the we will first see that particular glass or some material, transparent material, how much is the visible light transmission, which I want to improve. Okay. So, we will see how much is this visible transmission, how much percentage or how much, and out of that how much is your SHGC. SHGC will going to increase your temperature. So, this LGS ratio, light to solar gain ratio, how much is your light and how much your solar gain, what is the ratio between them. So, I want more light, I do not want the solar gain. So, if this ratio is high, if a particular somebody can give me a material, this glass material which has a high VT value, but low SHGC value, I will be very happy, because I will have lot of daylight, the visible spectrum will be much more, which will not going to increase my temperature, and also having the low SHGC value. So, the temperature increment will be low. So, we can have reflective glasses or clear double glazing glasses will follow this 45-degree path. So, both are equally increasing. Suppose a kind of a glass which is having a high SHGC, also the high VT, which is very normal, but some of the glasses may be show like that very high SHGC has very high low VLT, visual light transmission. So, we should not actually take those glasses, no, because that will unnecessarily increase my heat gain, but it will not give me any kind of the daylight, the low VLT. But I will be very interested if I get some kind of glass in this zone where I have a very high VLT, very high value of VLT and very low value of SHGC. Okay. So, that high VLT give me more daylight penetration, I will be very happy, because I will my artificial electrical the lighting load will be less, and I will not having that much of heat gain because the low SHGC value. So, there are some high performance tint glasses, there are some low, I just talk to you regarding that low emissivity glasses are there, which I can think of. So, it is another graph where we can see the from the wavelength point of view, the visible portion and the infrared. So, if you take a double glazed window glass or whatever, so it has a good visibility and also good infrared penetration. So, it is both are good, both VLT and the SHGCs are good, which is not going to be bothering me, because I am going to have the lot of heat gain. But I can actually go this kind of curved one, where we have a good visibility or the visible spectrum penetration, but very low kind of the infrared penetration. So, those are the low E glasses also. See the red color pattern is very high visibility or the low kind of a thing. So, these are the references for this lecture. I have used the same references, and what we understand from here is that the solar radiation plays a very important role. As you know, it is again a periodicity, it has a periodicity. So, we need to see that one in the following lectures, that how we can tackle that one, and increases the surface temperature of the wall, also it penetrates through the window. So, the transparent things like the window glazing, skylight has to be also designed accordingly. Thank you so much.